Hi folks, we're going to take a look at the solution of question 4 from the April 12th worksheet. So let's take a look at the question A here. It says find the point on the y-axis which is equidistant, okay, so that word means same distance, to each of those 2 points. So since these are points in 3 space, we assume that we're talking about that y-axis in 3 space. So if I draw myself a little picture here to help me out, okay, so x, y, z. Okay, so some point on the y-axis, well, what would that look like? Well, when you're on the y-axis, both your x and z components are going to be 0. So I'll call that middle component, I'll just leave it variable, so that's, I don't know where it is. So I'll just call that 0, y, 0. Okay, so I'll call this the point y. Okay, and I've got 2 other points. I'm not going to make any effort to be precise as to where I draw these points. And I'm trying to find this point on the y-axis such that these distances, okay, are the same. Okay, but how can we find the distance between 2 points? Okay, say this is A and that's B. Well, one thing we could do is we can join these points with vectors. So say consider the vector by and consider the vector ay, and the distance between the points will be just the same as the magnitude of that vector. Okay, and what we have to find is we have to find that y value such that the magnitude of the vector ay is equal to the magnitude of the vector by. Okay, so this is going to be our strategy for solving this. Let's say we call this A and we call that B. Okay. So let's start by finding the magnitude of ay. So let's find ay itself. Okay, so notice here how I try to set it up so that the variable comes first. That's why I did ay and not ya. Okay, so here let's do 0 minus 2, so that's negative 2. Y minus negative 1, so y plus 1. And then 0 minus 1, negative 1. So that's the vector ay. And now let's find the vector by. Okay, 0 minus 0, well, that's just 0. Y minus 1, and then 0 minus 3, negative 3. Okay, and so now we can find the magnitudes easily. So here we've got negative 2 squared is 4, plus y plus 1 squared, plus negative 1 squared is just equal to 1. And on the other side, well, we've got 0 squared plus y minus 1 squared, and then plus negative 3 squared, so that's plus 9. Okay, so let's now solve this here. So since we've got square roots on both sides, I'll square both sides of the equation. Okay, and while I'm at it in the next step, I'll also expand these 2 binomials. So here we've got 4 plus 1 is 5, plus, and y plus 1 squared is going to be y squared plus 2y plus 1. Okay, and then here what do we have? Well, we've got the 0. Here we've got y squared minus 2y plus 1 plus 9. Okay, and here I notice that the y squared on either side of the equation. Okay, so now let's solve. I can bring this negative 2 out of the other side, so I have 4y is equal to, so here I've got 10 and 5 plus 1 is 6 minus 6, so 4y is equal to 4, and so y is equal to 1. Okay, so if I take the point 0, 1, 0, it's the same distance to point A as it is to point B. Okay, so that's the solution for part A. Now in part B we see that it's generalized a little bit, because here it says determine all points which, oh okay, I just realized there's a little typo here in this question, so it should be determine all points which are equidistant to those 2 points. So let's which are, okay, I think I might have change this question around and I didn't look at the grammar. Okay, so here we're looking for all points which are equidistant to these 2 points. Okay, so not just the one. Okay, and let's just draw ourselves a little picture here to see how that might make sense. Okay, because if I were to draw these 2 points, whatever they are, well, you go, certainly there's that point in the middle which is equidistant to both. Okay, if you think of the midpoint like back in grade 10. Okay, but it doesn't say it has to be the smallest distance. What about that point there? That's also equidistant to both points, and that point there is also equidistant. Okay, so when it comes to two-dimensional coordinates here, well, I start to realize that there's a pattern, that anything along this line, okay, that runs in the middle of those 2 points, and it looks like it's going to have to be perpendicular to the line that joins them, anything along that line will have the same distance to either point. Okay, but now we're working with 3D points, so it'd be interesting to see what that would look like in 3D. Okay, so let's start by solving the problem. Okay, so now my point is not going to be the point 0, y, 0. It's going to be any point, okay, of the form x, y, z. Okay, so now I don't have any constraints on that point, okay, and I have to still connect that to point A, which is 2, -1, and 1, and to point B, which is 0, 1, 3. Okay, so I'm going to do the exact same thing as I did before. I'm going to connect point A to now point P, and B to point P, and I'm going to determine when the magnitudes of those vectors are the same. Okay, so here I have the magnitude of AP needs to be equal to the magnitude of BP. Okay, so now we've got the square root of x minus 2 squared, so second minus first, okay, plus y plus 1 squared plus z minus 1 squared. Okay, so I'm just finding the vector and then the magnitude. I'm just saving myself a little bit of time here. Okay, so here now let's do BP. So we have x minus 0 squared, okay, plus y minus 1 squared, and then z minus 3 squared. Okay, so again, I'm going to square both sides, and let's expand everything out. So on the left-hand side, we have x squared minus 4x plus 4, plus y squared plus 2y plus 1, plus z squared minus 2z plus 1. On this side here, we've got x squared plus y squared minus 2y plus 1, plus z squared minus 6z plus 9. Okay, and you notice, similar to before, that all the squared terms cancel out. Okay, now think about any type of problem like this. Well, that's always going to happen. Okay, because you've always got x minus or x plus something on either side of the equation that's being squared. Okay, so here the y squareds go and the z squareds go. Okay, so let's figure out what we have left. Well, we don't have any x component here, so here we just have negative 4x. Okay, let's bring the y's together. So here we got 2y plus the 2y there, so similar to what we had before. Whoops, 4y. And the z's, we have negative 2z, and if we bring that over, plus 6z, so plus 4z. So notice how I'm dealing with this like I would something with only 2 variables. I bring all the variables to one side, and let's bring all the numbers to the other side. Okay, so here we have 4 plus 1 is 5, plus 1 is 6, and then minus 1 plus 9 is 10, so 6 minus 10 is negative 4, and I end up with this equation, which I can simplify. So let me divide both sides by negative 4, so I end up with x minus y minus z equals 1. Okay, so it stands to reason that I would have infinitely many coordinates x, y, z that would satisfy the condition of being equidistant to A and B. Because again, if I just look in 2 dimensions, I have infinitely many solutions. Okay, so these components of that third point have to satisfy this equation. Now, I'm not going to say too much here, because this is one of these questions where I tell you to keep all this in the back of your brain, because this will come up again. I want you to think about what this equation looks like. Okay, and remember what we talked about, that in 2D, you could create a line that's equidistant from those 2 points. But what would happen, so let's say this, represents a line here, okay, this toothpick, and any point on that toothpick is going to be equidistant to both of those points. Okay, so even if this was in 3 space, even if these 2 points were up here, I could place that line between them. But now that I'm in 3 space, let's move this line at an angle. Okay, and I realize, hey, these points, all these points are also equidistant to those 2. Let me move this line at a bigger angle, again sticking out of the paper. All these points are also equidistant to both points there. This line here, sticking out, all the points are equidistant to those 2 points. So I want you to think about what shape would this create, okay? That would represent all the points which are equidistant to 2 given points. Okay, and that's where I'm going to leave this question. Okay, that's it.